Today, scientists are wrestling with a mind-bending possibility. What if the universe you see around you isn't real in the way you assume it is? With the James Webb Space Telescope exposing early galaxies that look older than expected and quantum experiments revealing patterns that shouldn't exist under classical physics, researchers are questioning whether our cosmos could be a kind of projection. It sounds more like science fiction than science, yet the mathematics continues to agree. Far from being dismissed, this strange idea is gaining traction, and it raises a deeper question about the true structure of reality. The holographic principle in 2025. Could everything we sense in 3 dimensions, every object, every particle, every distant galaxy, actually be a projection from a 2-dimensional surface we cannot directly see? That is the central claim of the holographic principle, and in 2025 it has grown into a serious framework for exploring the foundations of physics. The idea sounds abstract, but the principle itself is straightforward to describe. Our familiar universe might be an encoded image, much like a hologram projected from a flat boundary where the true information resides. Imagine an entire cosmos unfolding like a film on a screen, with stars, planets, and even ourselves existing as the projected narrative, while the genuine code sits beyond reach on a deeper surface. The origin of this concept traces back to puzzles about black holes. In the 1970s, researchers confronted a paradox. Quantum theory insists that information can never disappear, but black holes seem to erase it completely, swallowing matter and radiation into a hidden singularity. To solve this, Gerard T. Hooft and Leonard Susskind proposed that information might not vanish, but instead be stored at the boundary of a black hole, the event horizon. Later developments linked this to a broader picture. If all the data of a black hole could be inscribed on its surface, perhaps the same applied to the universe itself. This leap gained credibility in the 1990s with the formulation of ad-s-CFT duality by Juan Maldacena, demonstrating that in certain spacetime models, a universe with negative curvature, all the physics inside a volume could be equivalent to information written on its boundary. Our universe isn't an anti-de Sitter space, but the principle opened a path for extending holographic reasoning beyond that idealized case. Today, that line of thought remains central as physicists attempt to craft a working theory of quantum gravity. In 2025, research groups are testing whether this principle can move beyond mathematics into contact with actual observation. The James Webb Space Telescope plays a role here, though not by looking for holographic signatures directly. Instead, it supplies extensive data about how the early universe developed, how the first galaxies and quasars lit up, how reionization shaped the cosmos, and how structure emerged across space. These measurements inform cosmological models that holographic frameworks must be consistent with. In effect, Webb gives physicists the history book of the early universe, and theoretical models, holographic or not, must fit the narrative. It's indirect but crucial. Without accurate information about how matter and light behaved in the universe's first billion years, there is no way to judge whether holographic space is plausible. Theoretical work has also linked holography with quantum entanglement. Entanglement connects particles across distances so that their properties remain correlated in ways standard physics finds deeply counterintuitive. In 2025, this is no longer viewed as just a quirk of quantum theory. Physicists suggest that networks of entangled particles might stitch spacetime together, forming the fabric we move within. Experiments using photons across continental distances and analyses of astronomical photon streams point to patterns in correlations that look more systematic than chance should allow. Researchers at Utah State University, particularly physics faculty such as Verla and Cadiel, are pursuing this line by building mathematical models in which the holographic principle is not optional but mandatory. Their framework treats precise mathematical construction as a kind of laboratory apparatus. By working within these rules, they generate predictions about the physical world that can be tested against observational data. They argue that if a theory of quantum gravity is to be credible at all, it must contain a holographic property at its core. This approach reframes the holographic principle from speculation into a working component of testable physics. Evidence is also being explored through gravitational wave detectors. Instruments such as the GEO 600 facility in Germany were originally designed to capture faint ripples in spacetime from distant mergers, but they have revealed curious irregularities. These noise patterns have intrigued some researchers, who argue they are consistent with what one would expect if spacetime operates in discrete units rather than smoothly. The analogy is like zooming into a photograph until the pixels appear. You recognize the limits of resolution. In this view, space itself may behave as a pixelated projection, aligning with the holographic idea. But it is important to stress the interpretive caution. These signals could still have alternative explanations, and most physicists remain careful about jumping to conclusions. Yet the fact that such anomalies have not been conclusively dismissed keeps the topic in active discussion. This body of work connects directly to a larger challenge. uniting quantum physics and gravity. For decades, efforts such as string theory, loop quantum gravity, and emergent gravity models have sought to reconcile the rules of the very small with those of the very large. The holographic principle fits into this search by suggesting that gravity arises not as a fundamental feature, but as an emergent phenomenon, much like how temperature emerges from the average behavior of countless molecules. If this is correct, then space itself is not the stage of the play but part of the performance, weaving itself out of underlying informational relationships. That challenges everyday perception in a radical way, turning what we thought of as foundational distance, location, depth into derivative effects. Meanwhile, progress is not confined to theory and cosmology alone. In 2025, a breakthrough in optical engineering came from the University of St. Andrews, where researchers successfully combined holographic metasurfaces with organic light-emitting diodes. These thin-film devices, common in phone displays, were reimagined as tools for producing holograms. By shaping nanoscale structures on the metasurface, they controlled how light emerges from each pixel of an OLED, enabling entire images to be generated more compactly and efficiently than older holographic systems allowed. While this technology belongs firmly in electronics and optics, not cosmology, the conceptual overlap is striking. Here too, three-dimensional images are produced from two-dimensional information. The metaphor that once seemed far-fetched in physics also appears in tangible, consumer-oriented technologies. Taken together, the year's advances in theory, experiment, and technology reinforce the status of the holographic principle as a serious player in modern physics. The links from black hole paradoxes to add SCFT duality, the ongoing analysis of cosmic data from telescopes, the rigorous testing through mathematical modeling at Utah State, the unexplained signals in detectors, and even parallel developments in optics all illustrate that 2025 treats the principle not as science fiction, but as an active hypothesis. If these strands converge, our everyday view of depth and interiority, walking across a room, perceiving one object in front of another, might be revealed as only a kind of perceptual map, not a fundamental property of reality. Yet despite the steady accumulation of hints, we remain at the stage of possibility rather than certainty. All holographic evidence is indirect, whether extracted from cosmic background radiation patterns, statistical anomalies in entangled systems, or ambiguous detector signals. No decisive smoking gun has emerged. But what makes the present moment notable is that multiple independent research routes keep pointing toward the same principle. That sort of convergence often signals a turning point, when an idea once considered speculative moves closer to mainstream acceptance. And while questions about holography challenge the way we think about reality itself, they naturally connect to an even broader possibility. If information can shape space, then what happens if space is not singular, but part of a much larger structure? The next frontier of inquiry steps away from seeing only one universe and begins to ask whether ours might be just a fragment of something far larger. Eternal inflation and endless universes. The theory of eternal inflation introduces a striking possibility. Space may not have expanded only once in its earliest moments, but might still be undergoing that process in different places, producing separate, disconnected regions that each resemble distinct universes. In this framework, our visible cosmos is only one such region, a bubble formed when inflation slowed long enough for matter and radiation to condense, while countless other bubbles continue forming elsewhere. In this view, the universe is not a single entity, but an expanding background filled with isolated pockets, each with its own beginning and perhaps its own physics. To see why this proposal matters, it helps to recall the problems the original inflationary theory was meant to solve. Without rapid expansion, the universe today would look irregular, with matter clumped unevenly across vast distances. But inflation smoothed those irregularities, stretching out space so thoroughly that the cosmos appears flat and uniform on the largest scales. It also solved the horizon problem. Regions far apart in today's sky display the same temperature in the cosmic microwave background, even though they should never have exchanged information at light speed. Inflation accounts for this by postulating that those regions were once close together before expansion drove them apart. However, calculations showed inflation wouldn't necessarily end everywhere at once. Instead, it could pause in localized patches, allowing matter to condense into a bubble universe, while surrounding space continued to expand. That expansion, being exponential, would never stop in other regions, meaning new bubbles would continue to form forever. The outcome is what some physicists describe as cosmic foam, disjoint universes budding off endlessly from an inflating background. Our observable universe, complete with galaxies and stars, is hypothesized to be just one such bubble, cut off from others we can never reach. The challenge lies in evidence. If multiple universes exist, could traces of them ever reach us? One line of investigation looks to the cosmic microwave background, the faint glow left from when the universe was about 380,000 years old. The CMB is remarkably uniform, and this near-perfect uniformity became one of the strongest supports for inflation. Yet this same uniformity also poses a question when combined with another observation: hints of large-scale alignments or axes that suggest preferred directions in the CMB data. Cosmologists have also identified unusual cold spots, regions spanning degrees of sky that seem significantly cooler than statistical models would allow by chance. If these anomalies are real and not due to data processing or foreground contamination, they could be the fingerprints of bubble interactions, subtle signs that our universe once brushed against another. Over the past few decades, satellites like COBE, WMAP, and Planck mapped the CMB with increasing precision. None provided a decisive answer, but by 2025 the discussion remains unresolved. Analyses continue to reveal features that don't sit neatly with the simplest models of inflation. Some researchers interpret cold spots and cosmic axes as artifacts, while others suggest they may hint at collisions between universes in an eternally inflating background. The near-uniform distribution of the CMB temperature, which strongly resists explanations involving universal spin or rotation, complicates the story further, leaving no clear resolution. Adding to this debate is input from the James Webb Space Telescope. Webb's main focus is not the CMB itself, but its data on the first galaxies affect models of how the early universe evolved. By measuring reionization, the process when the first stars emitted radiation strong enough to strip electrons from neutral hydrogen, Webb helps refine our understanding of the conditions through which ancient cosmic light traveled. These refinements, in turn, shift predictions of how the CMB ought to look today. In particular, Webb's observations of how light escaped through the thick fog of early hydrogen have provided new challenges to existing models, forcing researchers to reconsider whether certain anomalies might be consistent with eternal inflation, or instead indications of more conventional processes. Alongside these observational puzzles is the problem of fine-tuning. The physical constants of our universe, the strength of gravity, the charge of the electron, the nuclear forces, lie in ranges that allow structure to form. Change them slightly and the cosmos might never have contained stars, planets, or living beings. Eternal inflation offers one possible explanation. If bubbles form constantly with varying conditions, then most universes would indeed be sterile. But with infinitely many attempts, a fraction would produce the right balance for complexity. Observers inevitably arise only in those few, making our universe's apparent precision less surprising. This reasoning ties closely to the anthropic principle. We should not be shocked to see fine-tuning, because only finely tuned universes contain beings able to notice it. While critics argue this feels less like a scientific prediction and more like a philosophical claim, for many theorists it remains a natural byproduct of eternal inflation. Another possible line of evidence concerns primordial gravitational waves. These ultra-low frequency ripples in spacetime would have been generated during the earliest instance of expansion, leaving behind a signature that later instruments might detect. If such waves were confirmed, they would offer strong support for inflation itself and could strengthen the case for its eternal continuation. As of 2025, however, no unambiguous detection has been made. Sensitive observatories continue searching, ruling out simpler inflationary models, but stopping short of confirming eternal inflation directly. This cautious progress has reinforced the scenario not by proving it, but by narrowing alternatives and leaving eternal inflation among the most consistent frameworks standing. Yet the theory raises paradoxes of its own. If inflation is eternal, then the number of universes it produces could be infinite. With infinity on the table, probability becomes impossible to handle in familiar ways. If every possible history happens somewhere endlessly, then there would be innumerable versions of us, each living slightly different lives in other bubbles. From a mathematical point of view, assigning probabilities to events in an infinite ensemble creates both philosophical and practical problems, since everything not forbidden would occur infinitely many times. Some physicists worry this undermines the scientific clarity of the framework, while others treat it as a challenge that future advances in probability theory might resolve. Despite open questions, what defines 2025 is that eternal inflation remains intact. Data have not erased it, nor have they confirmed it outright. Anomalies like the cold spot remain intriguing. Alignments on cosmic scales leave room for debate. Webb's findings complicate rather than simplify early universe physics. Gravitational wave searches narrow scenarios but stops short of definitive answers. Together, these threads keep eternal inflation active within cosmology, not proven, but not dismissed either, still offering one of the few approaches that can unite fundamental physics with the possibility of a multiverse. Thinking in these terms reframes our place in reality. Instead of a uniquely tuned cosmos, we may exist in just one instance of an unending process. The fact that our bubble supports galaxies, stars, and life becomes less a special stroke of fortune and more a natural consequence of vast numbers. In this sense, eternal inflation does not make existence less remarkable, but situates it within a framework where repetition and variation could be limitless. And although the evidence is ambiguous, such theories push physicists to confront unexpected questions, not only about what universes exist beyond our reach, but about whether the very reality we perceive reflects deeper structures yet uncovered. The simulation hypothesis revisited. What if the ground of existence is not particles or forces at all, but raw information processed through hidden instructions? This is the central idea behind the simulation hypothesis. The claim that our universe may operate like a coded system, its apparent physicality emerging from a deeper informational substrate. In 2025, the topic has re-entered mainstream discussions, not only due to philosophical curiosity, but because of new connections being made between quantum computing, high-energy physics, and the mathematical structures embedded in nature's laws. The once fringe proposition is being re-examined as our best tools for probing reality begin to reveal patterns that resemble limits not of physics, but of computation. The appeal lies in how these patterns emerge in precise investigations. Particle accelerators, which collide matter at extreme energies, continue to test the standard model by smashing together fundamental particles and observing the debris of interactions. This model has had extraordinary success, but its equations are complex, sprawling, and occasionally suggestive of hidden order. Experiments have revealed constraints and repeating boundaries, rules where certain energy values fail to yield physically consistent results. To computer scientists collaborating with physicists, it looks remarkably like the sort of resolution ceiling seen in simulations, where code cannot generate values beyond its programmed limits. More striking still are those apparent discontinuities in collision data, tiny gaps where certain states fail to appear. At first, most researchers treat these as nuisances, the sort of statistical noise that cleaner machines or sharper sensors will later erase. But advocates of the simulation hypothesis view these gaps differently. They compare them to the pixel effects seen in digital images. Zooming in close enough eventually reveals blocky boundaries where the smoothness breaks down. If spacetime were continuous at its foundation, no such missing states should exist. But Melvin Vopson, a physicist at the University of Portsmouth, has argued that if our universe really were a vast computation, such discontinuities would be expected. He suggests that a super-complex universe like ours would require built-in optimization and compression to avoid impossible resource demands in computational power and data storage. In his framework, the very gaps or pruning of states in nature could be signatures of this hidden efficiency, signs that the universe conserves information like a software system trimming files. This line of reasoning aligns with Vopson's broader claim known as the second law of infodynamics. He proposes that just as the second law of thermodynamics governs the increase of physical disorder, infodynamics governs information, forcing its entropy, the measure of disorder in data, to decrease over time. In principle, systems should move toward more optimized, compressed representations of themselves. He cites patterns in atomic transitions, genetic mutations, and even features of digital media where information appears to condense rather than endlessly scatter. According to Vopson, this is exactly what we are observing all around us, including in digital data, biological systems, mathematical symmetries, and the entire universe. He interprets this as evidence that the cosmos itself is engaged in data optimization, precisely what one would expect if it were computationally simulated. Not all agree, of course. Critics point out that many such trends have conventional explanations within thermodynamics, physics, and evolutionary biology. For instance, the apparent compression of data in genetic sequences might emerge from natural selection's tendency to eliminate wasteful structures, not from digital encoding. Opponents argue that leaping directly to the conclusion we are in a simulation skips too many intermediate steps. A statistical curve or decreasing entropy in a complex system can be interesting without being proof of an artificial cosmos. Still, the fact that debates now focus not on dismissing the idea, but on whether its evidence is correctly interpreted shows how the simulation hypothesis has edged closer to scientific conversation. The philosophical challenges remain formidable. Science is built on frameworks that can be tested and disproved. A hypothesis that can accommodate any possible outcome risks drifting out of science and into metaphysics. If the universe's rules are simulated, then every anomaly could be waved away as a feature of the program. That sort of flexibility undermines its credibility. Critics such as Paul Davies and George Ellis stress that unless evidence can distinguish between a real physical universe and a simulated universe, the claim lacks testability. Moreover, the argument risks infinite regress. If our world is simulated, then what created the simulator? And if that too was simulated, the regress spirals upward forever. For orthodox physics, these problems make the simulation hypothesis more thought experiment than real theory. Yet supporters note that even if unproven, the hypothesis has heuristic value. It sharpens the way scientists think about information, structure, and symmetry in nature. Just as the holographic principle turned a paradox about black holes into a tool for exploring quantum gravity, the simulation idea reframes questions about physics itself. Even if reality is not literally code, examining whether it could be code exposes the boundaries of what equations and experiments can handle. Some argue that if the universe could not be simulated, even in principle, that itself would reveal profound truths about its structure. Others take a more pragmatic view, using simulation as an analogy to test whether physical laws maintain consistency when stressed to their limits. History also enriches the debate. The idea of infinite, repeating, or layered worlds is not new. Ancient philosophers such as Anaximander speculated about countless worlds as early as the 6th century BCE. In later centuries, thinkers like William James introduced the word multiverse, and today its meanings stretch from cosmology to philosophy of mind. Seen in this long tradition, the simulation hypothesis is less an outlier than a continuation of humanity's attempts to explain why reality appears ordered and intelligible in the first place. Whereas the eternal inflation model imagines endless universes created by quantum fields, the simulation hypothesis imagines the same multiplicity through layers of computation. In both, the ordinary assumption of reality as singular and fundamental is challenged. Even within this skepticism, the hypothesis proves useful in motivating real experiments. Researchers continue to test for discretization effects in high-energy physics, precisely because seeing resolution limits or pixelation in spacetime would suggest something unexpected about the foundations of nature. Whether one interprets those findings through Vopson's infodynamics or through more conventional physics, the act of trying to detect them propels experimental design. Thus, while many physicists doubt we are simulated, they acknowledge designing detectors and simulations that deliberately seek such patterns is scientifically productive. Quantum computing also plays an indirect role. These machines are increasingly able to model physical systems with fidelity that classical supercomputers cannot match. For example, simulating large molecules or condensed matter phenomena used to be computationally impractical. Now, quantum systems produce accurate predictions, mirroring the behavior of nature itself. Each time a researcher runs such a simulation, it raises a subtle question. If computers built by us can recreate small patches of physics with such accuracy that experiments confirm them, then what do we mean when we say reality is real? The feedback cycle is impossible to ignore. We use computation to understand physics, the physics resembles computation, and then the possibility that physics itself is computation resurfaces. These reflections underscore why 2025 feels like an inflection point. Few, if any, scientists claim direct proof of our universe being simulated, but the hypothesis has carved out space as a serious analogy, one that informs research design and drives theoretical refinement. Where once it sat as untestable speculation, today it functions as a pressure test on physics itself. Its role may not be to confirm that everything is code, but to expose how physics behaves when confronted with maximal interpretative questions. Like the holographic idea, it functions more as a conceptual laboratory than as an answer. By this stage, the discussion no longer hinges on proving cosmic programmers. Instead, the emphasis has shifted to what the simulation argument teaches us about the informational character of physical law. Whether or not Vopson's second law of infodynamics gains traction, and whether or not the strange gaps in particle data prove enduring, the simulation hypothesis now operates as a lens for re-examining what counts as fundamental. From entropy in biology to discretization in spacetime, from symmetry in mathematics to fidelity in quantum simulations, the boundaries between information theory and physics are becoming increasingly blurred. The next step is less about cosmic coders and more about continuing to confront anomalies in our models of reality. Some of those anomalies arise in unexpected places, subtle mismatches in how the universe accelerates or how energy behaves on cosmic scales. The simulation argument may not resolve these issues, but it keeps alive the principle that we must always test the assumptions we make about what drives reality forward. And when new observations arrive, they often make those assumptions harder, not easier, to justify. Energy's mysterious acceleration. One of the most persistent puzzles in cosmology is why the expansion of the universe accelerates instead of slows. For years, dark energy has been treated as the explanation for that acceleration, a uniform pressure embedded in space itself, added into Einstein's equations as a cosmological constant. But by 2025, new results from telescopes and galaxy surveys are eroding the idea that this mysterious component is unchanging. What once looked fixed is showing signs of shifting. And if that proves correct, it would alter both our understanding of the past and our projections of the future. The story of dark energy took shape in the late 1990s, when astronomers studying distant Type Ia supernovae discovered that galaxies were moving away faster than expected. Instead of gradual deceleration under gravity, the universe was speeding up. To account for it, physicists revived Einstein's idea of a cosmological constant, an energy intrinsic to space that counteracts gravity. This constant became the keystone of the lambda-CDM model, the standard cosmological framework describing matter, and dark energy. For over 2 decades, the model has successfully predicted large-scale structures and cosmic background measurements. But the assumption that dark energy's density never changes has always been a key part of its success. In recent years, the James Webb Space Telescope has begun offering data capable of testing that assumption with more precision. By observing very faint, extremely remote supernovae, Webb has given astronomers a clearer record of how expansion behaved billions of years ago. Type Ia supernovae function as distance markers, and comparing their brightness with the redshift of their light reveals how fast space was stretching when the supernova exploded. Earlier instruments provided rough trends but left significant uncertainties. Webb's infrared capacity has narrowed those uncertainties and highlighted small mismatches between predicted and observed expansion, particularly for events that occurred 6 to 10 billion years after the Big Bang. These mismatches may represent the first observational hints that dark energy is not constant. That case has been strengthened by ground-based surveys such as the Dark Energy Spectroscopic Instrument, or DAISY, which began operating in northern Arizona. DAISY's maps of baryon acoustic oscillations, the large-scale ripple patterns left from sound waves in the early universe, create an independent record of cosmic expansion. Comparing DAISY's data with Webb's supernovae and with the cosmic microwave background has leaned toward an evolving form of dark energy. Statistical analysis in early 2025 indicated preferences for evolution at levels ranging from 2.8 to 4.2 sigma depending on the dataset combinations. Those values do not meet the customary 5 sigma threshold for discovery, but they are strong enough to demand attention. For the first time, a major cosmological survey has consistently suggested that dark energy may not be static across all of time. If this result continues to hold, then the consequences are far-reaching. A cosmological constant offers mathematical elegance, a single term plugged into relativity, leaving the equations otherwise intact. But an evolving component forces new physics. One class of proposals calls for quintessence, a hypothetical field whose energy density changes slowly over billions of years. In this view, expansion accelerates because of the field's repulsive effect, but the strength of that effect shifts as the universe grows. Another more extreme scenario involves phantom energy. Here the negative pressure becomes stronger over time so that acceleration accelerates even further. If unbounded, runaway phantom energy could eventually pull galaxies, stars, and atoms apart in what some call the Big Rip. At the other end of possibilities, dark energy might not last at all. If its value decays, the acceleration could diminish in the far future, perhaps even reversing toward contraction. These scenarios all depart radically from the neat predictions of a static constant. They also raise questions about modified gravity. Instead of invoking new fields or exotic energies, some physicists suggest the observed acceleration happens because general relativity does not apply on the largest scales. If gravity behaves differently at cosmic distances than it does locally, what appears to us as dark energy may be a misinterpretation of incomplete equations. Distinguishing between these ideas requires observations far larger and more detailed than any to date. That is where upcoming facilities will play a role. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, is tailored to explore dark energy. Roman's field of view will be 100 times wider than Hubble's, yet it will retain comparable resolution. Its surveys will map galaxy distributions and dark matter lensing in unprecedented detail, building a three-dimensional record of how matter has evolved and how acceleration has shifted over cosmic time. Combined with Webb's deep, narrow look, Roman will provide the wide-scale context to test whether the hints from DAISY and Webb form a consistent picture or merely local anomalies. This developing picture also loops back into the well-known Hubble tension, the mismatch between the value of the current expansion rate derived from the early universe and the value measured locally. Cosmic microwave background data suggest a lower rate, while supernovae and galaxy surveys yield a higher one. For years, no satisfactory explanation reconciled both sides. Now, the possibility emerges that the tension reflects real dynamism in dark energy. If the effect has evolved, then extrapolations based on a fixed constant would inevitably fail to align. Early modeling suggests that allowing for a variable energy density can ease the divergence between early and late universe measurements, a sign that the Hubble tension may not just be a quirk of data calibration, but a window into new physics. Of course, cosmologists remain cautious. Margins of error still leave room for conventional explanations such as dust obscuration or calibration missteps in brightness measurements. No single instrument or survey can decide the issue. That is why teams are layering different approaches, cross-checking Webb's supernovae against Dacey's baryon acoustic oscillations, comparing both to weak lensing data and folding in the CMB. Each method offers different systematic risks, so consistent outcomes across all three would greatly strengthen the case. Given how disruptive a variable dark energy would be for the lambda CDM model, physicists stress that only converging evidence will suffice. Nevertheless, the implications are striking. Under a permanent cosmological constant, the universe's future is simple and bleak. Acceleration never slows, galaxies drift apart, star formation dwindles, and the cosmos falls into a cold, dark emptiness. But if dark energy grows in strength, even atoms may eventually be destroyed by expanding space. Conversely, if it decreases, the universe may one day stop stretching and instead shrink, possibly leading to a collapse or bounce into a new cycle. These extreme outcomes, Big Rip or Big Crunch, were once fringe ideas, but in 2025 they are back under consideration, not because of mathematical curiosity, but because evidence now keeps them alive. Perhaps the most intriguing shift is conceptual. Dark energy has long been treated as a placeholder term, simply a fix inserted to make equations agree with observations. Now its role looks more fundamental. If it evolves, then it has properties, dynamics, perhaps even interactions with fields we have yet to identify. Understanding those features would become as essential to physics as understanding electromagnetism or nuclear forces. Some speculate that dark energy may connect to quantum vacuum fluctuations or to undiscovered particles beyond the standard model. Others suspect it could reveal flaws in general relativity when extended across cosmic distances. Whatever the truth, the idea of dark energy as an inert backdrop no longer suffices. It is important to emphasize that the scientific process here advances even if the new claims weaken. Eliminating alternatives is part of progress. If future results tighten the case for a true constant, then theories about evolving fields can be discarded with confidence. If instead, evidence continues to point to change, physics shifts into a new landscape with far broader consequences. Either outcome cuts away uncertainty and clarifies the model. In that sense, the unsettling possibility that the universe's expansion is not governed by a fixed term is not an obstacle. It is exactly the type of challenge that drives the refinement of theory. All of this underscores how fragile our assumptions can be when faced with sharper instruments and richer data. The confidence of 2 decades in an elegant cosmological constant has been unsettled by just a few years of increasingly precise observation. What once seemed like a settled framework must now compete with alternatives ranging from new forms of energy to modifications of fundamental gravity. And behind each of these debates lies a deeper theme. When information appears to vanish or behave in ways not captured by our current models, science must contend with the possibility that our most basic concepts still hide unrecognized gaps. Solving the black hole information paradox. What happens to information that falls into a black hole? Does it disappear never to be recovered, or does it remain somewhere hidden in the structure of spacetime? That single question has puzzled physicists for half a century and has come to be known as the black hole information paradox. It grew out of a clash between 2 pillars of science: Einstein's description of gravity through general relativity and quantum theory's insistence that information cannot be destroyed. If information does vanish in a black hole, then quantum mechanics is broken. If it survives, then our understanding of gravity is incomplete. For years, the paradox sat unresolved, a boundary line between known physics and unknown physics. In 2025, researchers are still chasing answers, but new observations suggest we might be closer to a solution than ever before. The root of the paradox comes from how black holes are defined. A black hole forms when matter collapses so tightly that not even light can escape the boundary known as the event horizon. Anything that passes this point, whether it is a star, a planet, or a passing particle, cannot return to the outside universe. From the perspective of relativity, the story ends there. General relativity allows all of that mass and its information to condense into a singularity of infinite density. But quantum mechanics has stricter rules. Quantum theory treats information as conserved. States of particles may transform, scatter, or combine, but you can always track the information content in principle. Nothing is ever fundamentally erased from the universe. That conflict is where Hawking radiation entered the picture. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum effects allow them to emit radiation, losing mass extremely slowly over time. This meant black holes should eventually evaporate, but the radiation carries no imprint of what fell in before. It is thermal with no distinguishing marks. When the black hole finally vanishes, all the information of what entered appears lost forever. That is the crux of the paradox. Quantum mechanics says this cannot happen, but general relativity paired with Hawking's analysis says it must. Decades of attempts to reconcile the two sides led to a jungle of theories, everything from possible baby universes inside black holes to strange surfaces storing information in hidden ways. None gained broad acceptance. What has changed recently is the arrival of gravitational wave astronomy. Ever since LIGO made the first detection in 2015, we have been able to listen to black holes colliding. When two massive holes spiral together and merge, they release a huge blast of gravitational waves, ripples in spacetime itself. These waves include a telltale sequence called the ringtone, a fading vibration as the final, larger black hole settles down. In 2025, physicists analyzing ringtone signals have noticed subtle irregularities not explained by simple models. The patterns suggest that newly formed black holes may carry tiny imprints of internal structure as they radiate, almost like faint echoes embedded in the waves. Some researchers interpret these traces as signs that information is not completely lost when the horizon forms, but instead encoded in the geometry of the black hole. If that interpretation holds, it means the paradox may not be as absolute as it once seemed. Proposed explanations have names that sound like science fiction, but are treated seriously in professional physics journals. One suggestion is the holographic firewall. The firewall idea states that the horizon might not be the smooth, invisible surface general relativity describes, but instead a fiery boundary where quantum effects erupt. Information would not disappear inside, but would be imprinted or scrambled on this boundary. Another idea focuses on so-called quantum hair. Classical black holes are described by only three properties: mass, charge, and spin. Everything else is hidden. Quantum hair would add extra subtle features, subtle ripples on the horizon that record information about the contents. From a distance, they would be nearly impossible to detect, but in principle, they could allow conservation of information. The detection of small quantum-level irregularities in gravitational wave signals is precisely the kind of evidence one would expect if quantum hair exists. The holographic principle adds further support. If the information describing three-dimensional space can be represented on a two-dimensional surface, as holography suggests, then black holes might function in the same way. Every bit of matter that falls into one could be preserved as a pattern on the event horizon, the way a hologram encodes a three-dimensional image on a thin film. In that framework, Hawking radiation is not informationless after all. The radiation may look thermal at first glance, but with sufficient precision, correlations might be present, carrying a scrambled record of what fell in. Extracting such signals in practice would be staggeringly difficult, but technologically impossible is not the same as physically impossible. The fact that the mathematics allows it indicates the paradox may not be fatal to quantum physics after all. Debates remain intense. Some researchers insist the gravitational wave data are not yet sufficient to claim anything specific about information. The irregularities might be noise, or they might reflect limits of current detectors. Yet the same anomalies recurring across different events force scientists to keep them in consideration. Others argue that firewalls are too violent, clashing with relativity's claim that matter falling into a black hole experiences nothing unusual at the horizon. Reconciling both views may require new physics. Attempts to unify relativity with quantum theory under quantum gravity could offer that bridge, and the black hole paradox serves as a guiding test for those models. Whether through string theory's holographic dualities, loop quantum gravity's discrete spacetime networks, or other imaginative proposals, researchers are using the paradox as the critical problem their theories must resolve. In 2025, theoretical progress has married with computing advances. Simulations of black hole mergers now include quantum effects approximated through advanced coding methods and machine learning. These models produce ringtone profiles more closely resembling the observed irregularities, supporting what gravitational detectors record. While simulations do not prove reality, their alignment with data strengthens the idea that quantum structures are influencing macroscopic black hole behavior. This is important because black holes are some of the only environments where gravity and quantum mechanics operate at nearly equal importance. In laboratories or on Earth, quantum rules dominate. In galaxies, gravity dominates. Only at black hole horizons do both converge. That makes them natural testbeds for discovering the bridge physics has lacked for more than a century. It is also worth considering that a clear resolution may not involve one particular mechanism alone. Quantum hair, holographic storage, and Hawking radiation-carrying correlations may all turn out to be different perspectives of the same underlying rule. The paradox may dissolve not through one flashy theory, but through several pieces fitting together, all showing that the feared destruction of information never occurs. If that outlook proves right, the universe might be more orderly than the paradox first suggested. Information is preserved, only hidden and scrambled in ways previously unimagined. Over time, this realization would have broader implications beyond black holes. Cosmology, thermodynamics, and even ideas about time's arrow are tied deeply to the flow of information. Proving it is indestructible under the most extreme conditions would only deepen its central role in nature. For now, the paradox is not yet solved, but it is no longer just a philosophical riddle. Physical traces, subtle patterns in radiation and ripple signals are hinting that black holes are not the ultimate destroyers of information they once seemed. Instead, they may be strange libraries, messy and chaotic, yet still consistent with the unbreakable rules of quantum mechanics. That shift in perspective is immense. It means some of the universe's darkest objects, often described as devourers of light and matter, may paradoxically be guardians of information itself. And the faint echoes hidden in spacetime vibrations are the breadcrumbs leading physicists toward understanding just how that works, one collision at a time. Galactic spin and universal patterns. Galaxies, according to everything we thought we understood, should form with no preferred spin direction. The universe on its largest scales has long been assumed to be isotropic, meaning that no orientation or axis is more important than another. The principle of isotropy was central to standard cosmology. Yet when astronomers used the James Webb Space Telescope to examine vast surveys of galaxies, a strange detail emerged. Instead of a random scatter of spin directions, there appeared to be a subtle but measurable preference. Across thousands of galaxies, the same twist showed up more often than chance alone would predict. The spins weren't truly uniform. They leaned toward a global pattern that stretched across distances where no local effect should dominate. In other words, the distribution of galactic rotation was showing signs of coordination at scales beyond what mainstream theory comfortably explains. This surprising result does not mean every galaxy looks the same or spins in lockstep. Galaxy formation is still messy, bound up with the collapse of matter, flows of gas, mergers, and the influence of dark matter halos shaping the outcome. What makes the finding unusual is that when the tally of orientations is scaled up to thousands of systems, the asymmetries add up. Statistically, there should be no net bias. Yet Webb's catalog shows that bias again and again. In cosmology, this kind of preferred direction contradicts the assumption that the universe, born in an early hot dense state, expanded uniformly without selecting particular orientations. Those initial conditions underpin models of the Big Bang. If isotropy does not hold on the level of galaxy spins, then something about those conditions may need revision. One way to frame this challenge is simple. Isotropy says no direction is special. A preferred spin direction says some direction is. That is not a subtle difference. If galaxies throughout the observable universe oriented themselves more often one way than the other, then spacetime itself may carry memory of the universe's earliest moments, long before galaxies existed. The signal could be fossilized, imprinted in the geometry of the cosmos. Yet this idea runs against the grain of everything inflationary cosmology has argued, since inflation was supposed to stretch away any primordial structure. If something survived, it means inflation was incomplete, anisotropic, or guided by a rotating frame deeper than we expect. The entire framework of current theory, built on the foundation of isotropy, stands to be tested. The question then becomes, what could possibly explain such a preference? The first class of explanations remains mundane. Survey errors, calibration issues with Webb's images, or misidentifications of rotation based on galaxy morphology could, in principle, mimic the effect. But independent checks have continued to show that the signal remains even after correcting for these. If it is not an artifact, then more radical proposals come to the table. One idea is that the universe itself might be nested inside a rotating black hole. That picture suggests that what we perceive as cosmic expansion could be a manifestation of the geometry inside such a system. If the parent black hole carries angular momentum, a global spin could be imparted to everything inside. Rotation at the largest scale would trickle down to the galaxies, subtly biasing their motions billions of years later. Another possibility is large-scale anisotropy not tied to black holes but to the fabric of spacetime itself. Perhaps the universe had a preferred axis of rotation from the start, a cosmic spin imprinted at the birth of the cosmos. Theoretical models of such anisotropy exist, though they struggled for attention while isotropy reigned. In those scenarios, cosmic microwave background radiation should carry detectable traces, patterns aligned with the anisotropic axis. Curiously, the CMB does hint at large-scale anomalies, sometimes described as the axis of evil, alignments in the fluctuation map that should not statistically occur. These strange alignments, noted but often debated, could be related to the spin findings. Put together, they build a case that the universe may not be the uniform, featureless expanse standard theory imagined. If true, the implications would reach every part of cosmology. Cosmological constants might not be constant after all, but modulated by orientation. Models of structure formation, which assume randomness in spin distribution, would need revisions to explain how angular momentum emerges at galactic scales. Even the interpretation of cosmic acceleration could shift if expansion rates varied depending on direction. In essence, anisotropy challenges the Copernican principle, the belief that we occupy no privileged position in an undistinguished patch of the cosmos. If one axis or direction is special, then our observations are tied to it, and our place in the universe becomes a reference point relative to a larger geometric structure. Testing these bold scenarios requires further evidence. That means expanding beyond Webb's growing catalog, using planned surveys from instruments like the Vera-Rubin Observatory and Roman Space Telescope to trace orientations across even broader spans of space. If the pattern holds across independent methods and deeper redshifts, then theorists cannot ignore it. For now, these clues remain subtle, probabilities rather than certainties. But the more galaxies observed, the harder it becomes to dismiss the preference as coincidence. Science thrives on repeatability, and repeating patterns in galactic spin may become one of the clearest signs, yet that something foundational is missing in our picture. Community remains cautious, as it should. After all, history is full of anomalies that disappeared as data improved. Still, it is rare for patterns to persist across different telescopes and analysis teams. That resilience is what lends these findings weight. For many, the bigger lesson may be that cosmology cannot be content with repeating assumptions, no matter how elegant. The universe has a way of intruding with facts that upset symmetry and beauty. The simplicity of isotropy appealed for decades. Yet Webb's window into galactic birth and structure now opens the possibility that symmetry was never complete to begin with. Another crucial perspective is how galactic spin relates to dark matter. Galaxies form in dark matter halos, massive invisible structures that dominate gravitationally. The halos dictate how gas collapses, how stars ignite, and how spin begins. If halos share some asymmetry at formation, then spins aligned with that asymmetry could be natural consequences. For that to scale across cosmic distances, however, dark matter itself would need anisotropic properties. Typical models present dark matter as cold, collisionless, and isotropic. If rotation bias appears, then dark matter properties must adjust accordingly. In this way, the issue of spin crosses into the broader search to understand dark matter itself. There is also the possibility that spin preference offers a living clue about conditions before the observable universe. Inflation theory assumed an origin point smoothed to near uniformity by expansion. If instead inflationary energy fields carried rotation or preferred structure before expansion, remnants might survive. The memory of that state could be encoded inside the motion of galaxies, billions of years after inflation supposedly erased all differences. In that sense, galactic rotation is a fossil not of stellar evolution, but of events before the Big Bang shaped matter into the universe we see. Studying spin could become a path into eras long thought erased. If galactic spin preference is real, it forces a rethink of one of the simplest and most guiding assumptions of all cosmology. More than just a technical curiosity, it would directly contradict the statement that the universe looks the same in every direction on large scales. It would hint strongly that our models miss something foundational, perhaps something linking the nature of spacetime itself to rotation. That missing piece could fundamentally alter how we understand the birth of the universe, its stability today, and its ultimate future. The orientation of galaxies may be more than an outcome of physics as matter cooled and collapsed. It may be a message, a whisper from the universe's earliest moments, still spinning in plain sight. So the twist is this: galaxies, the vast systems we believe to be scattered with equal randomness, may actually be tracing out a deeper rotation written into the cosmos itself. And if that is true, then the universe carries scars of its birth that inflation failed to erase, scars hidden not in radiation or in expansion curves, but in the quiet rotations of galaxies turning slowly across the sky. Gravitational waves reshape cosmology. What can ripples in spacetime tell us about universes we cannot see? That is the driving question behind gravitational wave astronomy in 2025. Just a decade ago, gravitational waves were treated as exotic signals, flashes of cosmic violence produced when black holes crashed together or neutron stars spiraled into one another. Detecting them was celebrated as a triumph of engineering and theory, but the events were considered rare and isolated. Since then, the technology has advanced, instruments have improved, and a quiet shift has taken place. Gravitational waves are no longer occasional curiosities. They are becoming precise tools, providing a window into realms otherwise off-limits. And while they continue to confirm expectations about black holes and neutron stars, there are now whispers in the data that may point somewhere far stranger, perhaps even to signs of physics beyond our universe itself. The basics are straightforward. When a massive object accelerates, it shakes the geometry of spacetime. In normal conditions, the effect is so small it never registers. It takes extreme systems, like merging black holes containing dozens of solar masses, to generate ripples strong enough to detect. LIGO, Virgo, and later KAGRA were the instruments that first picked up those ripples in 2015, launching a new era in astronomy. Since then, an expanding global network of detectors has recorded dozens of collisions, cataloging them with growing detail. These detections demonstrated conclusively that black holes exist in populations larger than imagined and that they frequently merge. But as more events were stacked together, researchers began to notice something in the background. Even between the loud collisions, a quieter hum appeared to be present, a diffuse gravitational wave background filling space. The source of that background has become one of the biggest questions in cosmology. In 2025, detectors achieved enough sensitivity to analyze this background with greater depth. What they found deepened the mystery. Part of the hum can be explained by the accumulation of countless distant black hole mergers too faint to resolve individually. But the strength of the background appears to exceed predictions of that scenario, especially at certain frequencies. That excess suggests something else is contributing, something not accounted for in models of ordinary astrophysical events. This is where speculation about hidden histories or even hidden universes enters. Some physicists argue the signature could be consistent with collisions of primordial black holes, hypothetical relics from the early universe formed before stars or galaxies existed. Others suggest the anomalies could be much more radical, possible traces of bubble collisions between distinct universes in a multiverse setting. Primordial black holes offer the more conservative possibility. If extremely dense fluctuations existed just after the Big Bang, some regions could collapse into black holes of various sizes. Unlike the stellar black holes observed today, which require stars to form, primordial ones could range from asteroid size to larger than the Sun. Populations of such objects might create a gravitational wave background with properties different from ordinary black hole mergers. In particular, primordial black holes colliding in the infant cosmos would have generated signals spread across frequency ranges detectable today. This idea also ties into dark matter research. If primordial black holes exist in large numbers, they could account for at least part of the dark matter that permeates galaxies. That would solve two mysteries at once, linking the gravitational wave background with one of the most elusive cosmic ingredients. The more provocative interpretation looks outside our own universe entirely. If eternal inflation is correct, then bubble universes constantly emerge in an inflating background. Normally, these bubbles remain disconnected, causally isolated from us. But collisions at the boundary during formation could leave faint imprints detectable across cosmic time. One way such events might be registered is through gravitational waves. Unlike photons, which scatter and lose information when matter absorbs or irradiates them, gravitational waves travel largely unimpeded once generated. That makes them near-perfect messengers from the deepest past. If there were bubble collisions, they would have released bursts of spacetime ripples, and those ripples might still wash through detectors today. The anomalies now reported in 2025 do not prove this scenario, but their existence keeps the door open. For anyone wondering how a multiverse could ever leave experimental evidence, this is the kind of data scientists point to. Crucially, gravitational wave astronomy is still young. The sample sizes remain small, and with more detectors now under construction, the quality of evidence should improve within the next decade. When signals are faint, spurious noise always risks confusing the picture. Instrumental vibrations, local seismic effects, or even quantum fluctuations in laser measurements can create patterns mistaken for cosmic hum. That is why confirmation from multiple observatories matters. If the same irregular background shows up across independent facilities on different continents, confidence grows that it is real. And that is exactly what seems to be happening in 2025. The alignment across detectors strengthens the sense that this is not an artifact. What remains at issue is whether the source is astrophysical, primordial, or something more. Consider the broader shift this represents. For centuries, observational astronomy relied on visible light. Radio, X-ray, and infrared astronomy expanded the range, but detection still centered on photons. Photons scatter, absorb, and redirect easily, so astronomers are limited by the medium through which light travels. Gravitational waves, by contrast, cut straight through matter with minimal interaction. They carry pristine information from events inaccessible to telescopes. As these instruments improve, gravitational wave astronomy is no longer just a method to catch cataclysmic encounters. It becomes a precision tool for probing structures hidden behind light horizons. In practical terms, this could allow cosmologists to reconstruct events from the first trillionth of a second after the Big Bang, eras utterly opaque to electromagnetic observation. If gravitational wave backgrounds contain fossil signatures from before inflation, then experiments will soon be brushing up against data from prehistory itself. The suspicion that the background might involve signals beyond our universe forces cosmologists to weigh competing models carefully. Remaining cautious is essential because claims this bold can collapse under better resolution. But there is also precedent for discoveries arriving unexpectedly out of unexplained hums. The cosmic microwave background itself first appeared as an excess of radio noise in 1964, before being recognized as the afterglow of the Big Bang. Today it is one of the most studied signals in science. Gravitational backgrounds could follow a similar path. What begins as unexplained static becomes a fundamental window on reality. The interesting part is that unlike CMB radiation, which originates at the time atoms formed, gravitational waves could reach back further, perhaps as far as Planck scale physics. That possibility explains why so many theorists are watching these early anomalies closely. It may seem surprising that faint ripples barely moving detectors can carry information about realities as large as a multiverse. Yet that is the strength of gravitational waves. They couple directly to the geometry of space itself, so what they record is not filtered through matter or light. Any hidden structure in spacetime has the potential to reveal itself this way. Whether through primordial black holes, exotic particle transitions in the early universe, or bubble universes brushing against one another, all those scenarios leave distinct oscillatory fingerprints. The challenge is simply distinguishing which fingerprint we are observing. As sensitivity rises and more events accumulate, clearer answers should emerge. By then, gravitational wave astronomy may be playing a role as central as traditional starlight once did in guiding theory. All of this underscores an emerging theme. Cosmology is transforming from a field guided primarily by visual telescopes into one integrated with new messengers. Alongside neutrino astronomy, cosmic rays, and high-energy particle experiments, gravitational waves enlarge the toolbox of science. And while neutrinos or rays often arrive sporadically and interact weakly, gravitational waves permeate spacetime continuously. That means the background is always there, waiting to be measured ever more clearly. Each improvement strips away uncertainties about the universe's earliest conditions. Each suspected anomaly pushes the boundary of what counts as observable. The mini payoff here is striking. For the first time in history, humanity may possess tools capable of experimentally probing whether universes beyond our own have ever brushed against us. Gravitational wave astronomy stands as the bridge between pure mathematical speculation and measurable signals. It will take years to confirm what the anomalies mean, whether they point to primordial black holes or hints of parallel bubbles. But in either case, the message is the same. Ripples in spacetime are not just echoes of things we already know. They might be the first tangible evidence pointing beyond our cosmic horizon, hints of structures far larger than our universe alone. Quantum physics meets cosmology. Could the behavior of the smallest particles in existence hold the key to understanding the structure of the entire universe? That question sits at the junction of quantum physics and cosmology, and in 2025, the boundary between the two fields is no longer sharp. For much of the 20th century, physicists treated them as separate domains. Quantum theory dealt with fundamental particles, their interactions, and the strange rules that govern them. Cosmology worked on the largest scales, galaxies, clusters, and the overall geometry of space. But recent experiments suggest that the universe may not be divided so cleanly. Instead, the fabric of spacetime itself could be built out of quantum processes that link the smallest phenomena directly to the grand structure of the cosmos. At the center of this discussion are new entanglement experiments. Entanglement is the quantum property where two particles once linked remain correlated no matter how far apart they move. Change the state of one and the other responds instantly, even across astronomical distances. This effect, which seemed more like a philosophical puzzle when first proposed, is now tested with routine precision in laboratories. But in 2025, researchers began taking entanglement out of the lab and into much larger arenas. Instead of relying on photons within a single facility, teams have entangled photons separated by huge distances, linking light traveling between satellites, ground stations, and even from astronomical sources. Some experiments use starlight filtered from quasars billions of light years away to set the conditions for entanglement measurements. By incorporating cosmic light, scientists try to close loopholes in quantum tests that suggest possible hidden variables. The results consistently reinforced what quantum mechanics predicts. Entanglement appears genuine with no hidden cause. But beyond confirming quantum strangeness, these experiments hinted at something else. They showed suggestive signs that patterns of entanglement behave like maps of geometric relationships, as though spacetime itself emerges from an underlying network of entangled links. This idea is known as emergent spacetime, and it challenges the traditional view of space as fundamental. In classical physics, space is a stage on which events take place. In quantum physics of particles, the stage is assumed to exist already and the particles move inside it. But if space is emergent, then the stage itself is projected from relationships between quantum states. Imagine a web built from threads. The familiar structure of spacetime with distances and dimensions could be a large-scale illusion, arising out of the connectivity of the threads rather than existing independently. Entanglement offers a possible mechanism for those threads. When particles are entangled, they behave as if directly linked regardless of separation. Extend those links to huge numbers of particles, and the pattern they create may be what we interpret as geometry. In 2025, studies using networks of entangled photons support this by showing correlations matching mathematical models of space emerging from entanglement patterns. One source of motivation for this line of thought comes from black hole research. The black hole information paradox discussed earlier highlighted the idea that information might be stored on surfaces in holographic form. Entanglement has been tied to that solution because some theorists propose that wormhole-like connections, called Einstein-Rosen bridges, could be equivalent to entangled particle states. The slogan is sometimes phrased as equals EPR, connecting bridge geometry with quantum entanglement EPR. If that equivalence is more than metaphor, then spacetime features like wormholes or horizons are just different expressions of entangled states of quantum systems. In this way, microscopic correlations explain apparently macroscopic geometry. The fact that experiments now demonstrate entanglement over astronomical baselines suggests that this principle is not just mathematical convenience, but an active property of the universe. These developments frame a tension. For most of modern physics, quantum theory and relativity stood as separate languages. One governed the small, the other the large. Uniting them was the dream of quantum gravity, but attempts like string theory or loop quantum gravity rarely produced testable predictions. Emergent spacetime through entanglement seems to change that. It suggests an experimental bridge. When entangled photons measured over distances of hundreds or thousands of kilometers show consistent behavior, those correlations match predictions from models that try to generate geometry from entangled structures. That means tests once thought too abstract for experiments are creeping into measurable science. If further experiments extend entanglement to greater distances and keep finding regularities that match emergent spacetime models, then cosmology may gain direct data about its deepest foundations. Another implication is the reframing of what empty space means. Traditional physics describes vacuum as emptiness, occasionally disturbed by quantum fluctuations. Emergent models say vacuum is itself the web of relationships between quantum states. Distances and directions are not intrinsic, but arise from the way entanglement spreads across the system. Space, in these theories, is a derived property. The entanglement network acts like scaffolding, and the geometry we observe is simply the large-scale manifestation of its connectivity. This helps explain puzzles such as why gravity is so weak compared to other forces. Gravity would not be a separate fundamental force, but the statistical outcome of the way geometry emerges, an echo of entanglement patterns rather than a standalone interaction. In this sense, gravity is not something added, but something that results inevitably if space emerges from quantum links. The experimental hints are faint, but they are measurable. Quantum communication networks spreading across Earth and orbit now provide real-world applications while also serving as labs for fundamental questions. Satellite-to-ground entanglement allows photons to remain correlated despite atmospheric interference and orbital distances. If those photons remain linked long enough, and their measurement outcomes continue to agree with entanglement predictions, then those tests strengthen the view that entanglement is robust even at continental scales. Researchers have even begun associating expansions of these networks with direct analogs of space being constructed. Each new node functions like adding a piece of geometry. Shifts in network connectivity could, in principle, resemble perturbations of spacetime. While analogies must not be overstated, the resonance between technological development and theoretical proposals is striking. Why does it matter that space could be emergent rather than fundamental? The most direct reason is that it may finally explain how quantum physics and gravity fit together. If geometry arises from entanglement, then general relativity is not discarded but explained as a large-scale expression of quantum rules. Instead of two conflicting theories, they become layers of the same structure. This could help solve long-standing paradoxes like those around black holes, but also clarify cosmic evolution and expansion. In fact, emergent models predict subtle deviations from uniform expansion, possibly linking to recent puzzles with dark energy measurements. If experimental anomalies continue to align with these deviations, emergent spacetime could transition from philosophical speculation to mainstream cosmological model. Still, skepticism remains strong. Many cosmologists argue that entanglement results may be remarkable, but attributing the entire structure of spacetime to those results is premature. The mathematics is still incomplete, and experiments have not ruled out simpler interpretations. Some of the correlations seen may be explainable as conventional quantum behavior without needing the leap to claiming space is emergent. Others caution that entanglement experiments are still vulnerable to loopholes or biases. The cosmic photon tests, though ingenious, are also difficult to implement with full reliability, and statistical errors grow with distance. That means confirming emergent spacetime predictions may require decades of improved experimental control. The tension between speculative ambition and cautious science is clear. On one hand, the notion that the universe's geometry is sown from entanglement seems extraordinary, almost too bold. On the other hand, the fact that experiments designed to test unrelated questions are accidentally supporting those predictions gives weight to the idea. An ordinary interpretation would simply say quantum theory is robust across scales. The radical interpretation says quantum theory is not just robust, it is foundational, and everything else, including space itself, is just its consequence. Which view prevails will depend on evidence yet to come. The practical side of this situation is that quantum physics is no longer constrained to microscopes and particle accelerators. Its reach extends across satellites, global networks, and astronomical sources of light. By incorporating these scales into experiments, physicists are beginning to test hypotheses that tie particle behavior directly to cosmology's largest questions. In a sense, the tiniest particles are starting to reflect the entire cosmos, not metaphorically but operationally. Their correlations may encode the very geometry that we walk through each day. For the first time, quantum experiments are giving measurable insight into the structure of spacetime itself. No longer confined to thought experiments or tabletop devices, they are shaping the way humanity writes its story of the universe. Future cosmic endings reconsidered. Will the universe end in endless cold, a violent tear, or by some route that no one has yet imagined? For more than a century, those have been the basic possibilities physicists debated. The most traditional view was a slow fading called heat death. Over trillions upon trillions of years, stars burn out, black holes evaporate, and energy spreads so evenly that nothing interesting can happen anymore. The universe would not end in fire, but in silence. Then, as theories about accelerating expansion gained traction, a darker possibility emerged. What if expansion speeds up so much that it rips apart galaxies, stars, planets, even atoms? That scenario came to be called the Big Rip. And third, a long-standing alternative said expansion might eventually stop and reverse. If gravity reasserts itself, the universe could collapse down again in a big crunch, with the chance that a new cycle begins from that collapse. But in 2025, the picture of how the universe might end has become messier. The discovery that dark energy may not be constant calls every one of those older certainties into question. The core reason some scientists worry about a big rip is the possibility of phantom energy. Phantom energy is a form of dark energy in which the repulsive effect grows stronger with time, instead of staying stable. As expansion gains speed, matter structures lose their grip. At first, galaxies drift apart and galaxy clusters separate. Later, individual galaxies come unbound as stars drift farther and farther away. At the most extreme stages, planets lose their orbits, atoms stretch, and eventually even nuclei break apart. It is a vision of destruction on every scale. This prediction is not speculative fantasy, but the logical outcome if dark energy takes the form of phantom energy. Until recently, the difference between a constant vacuum energy and phantom energy seemed marginal. Small variations in the strength of acceleration were easy to hide within error bars. But in 2025, improved data from Webb supernova measurements began to show slight deviations hinting that acceleration could be evolving. Immediately, attention turned to what that might mean for the universe's timeline. Simulations run with these new data sets suggest alternate endgames. If the trend lines for dark energy point toward negative pressure growing stronger, then phantom energy might indeed dominate. Computers tracing billions of years of evolution show an acceleration curve that keeps rising, dragging expansion into a runaway effect. Depending on how steep those measurements truly are, the timeline could mean galaxies pulled apart hundreds of billions of years from now, down to a catastrophic end in less than trillions. But if the slope is shallow, the universe might coast along mostly unchanged for many ages before that fate. These are not predictions carved in stone, but they do illustrate how sensitive the endgame is to small differences in dark energy's behavior. The key discovery of 2025 is that dark energy may not be as fixed as scientists once believed. That alone is enough to throw cosmic endings into doubt. Of course, phantom energy and big rips are still not the only outcomes that make sense in models. Some simulations show the acceleration tapering off. In that situation, expansion continues but slows toward a more balanced rate. The result is a universe that does not crunch or rip but enters a freeze. Stars run out of fuel, black dwarfs form, and black holes dominate. Even those eventually radiate away through Hawking radiation, leaving only a thin bath of dilute particles. That leads to the quiet vision of heat death. In such a universe, entropy keeps increasing until no energy is available to sustain any structures. The time horizon for heat death is staggering, far beyond current scales of imagination, but it remains the default outcome if dark energy holds steady or weakens slightly over time. For decades, it was seen as the most likely ending since data suggested a cosmological constant. But that assumption is no longer as secure. There is also the possibility, though less favored, that dark energy is not only evolving but may one day reverse. A decay of vacuum energy or a shift in some underlying field could result in repulsion turning to attraction. That would signal the beginning of a cosmic retracing. Expansion would slow, then stop, then switch directions. Galaxies that drift apart for billions of years might eventually begin to move closer again. Structures could collapse inward, temperatures would rise, and the universe's timeline would accelerate toward a crunch. Far from the cold emptiness of heat death, this would end in a crushing implosion. Some models even allow for a bounce. In those, the collapse compresses everything back to extreme density, producing initial conditions for a new expansion cycle. If correct, then the universe may not have one beginning and one end, but infinite cycles of birth, growth, collapse, and rebirth. These ideas have been discussed for decades. What has changed now is that evolving dark energy provides a mechanism. If energy densities shift sign, then phases of expansion and contraction can alternate, producing a dynamic rather than a static long-term history. 2025's focus on simulations comes from access to better computing power and better inputs. Older predictions about cosmic fates relied heavily on broad assumptions. Now, with Webb data on early galaxies and supernovae, baryon acoustic oscillation surveys, and gravitational wave detections of mergers, scientists can feed far more precision into their models. The results do not converge on one favored ending. Instead, they reveal how wildly different small differences in dark energy behavior can play out. Slight increases in its strength over time tilt the future toward a rip. Slight decreases load the path toward slowdown and crunch. And values resting nearly flat stretch out into a freeze. Which path unfolds depends entirely on whether dark energy evolves, and if so, in what direction. The dread this inspires is easy to imagine. Heat death is a future of stillness, but at least it occurs slowly, on timescales so vast they make any human anxiety seem irrelevant. A big rip, however, is dramatic. Even though it would still occur unimaginably far away on human scales, the concept of the universe tearing down to its smallest components feels catastrophic. A big crunch sounds equally violent, reversing everything into a collapse. But dread should not be mistaken for inevitability. The truth is, every option is tied to uncertainties about dark energy. And that uncertainty is growing more interesting, not more stable. Each new round of data complicates the picture instead of resolving it. Even in 2025, cosmologists admit they do not know which future is most likely. All they know is that the fate of every star and galaxy depends on the behavior of something no one has yet explained. There are also other, more exotic theories circulating. One suggests vacuum metastability. In that case, our current vacuum state of the universe is only temporary. At any moment, it could tunnel into a lower energy state. If that occurs, a bubble of new vacuum forms and expands at the speed of light, destroying all structure inside it. This collapse would rewrite physics itself, annihilating all atomic and subatomic structures instantly with no warning. Though terrifying, this possibility arises naturally out of some particle physics equations and Higgs field considerations. The probability is low and no evidence confirms it, but its existence as a theoretical possibility adds another option to the growing list of cosmic doomsdays. In stark contrast, other scientists work on cyclic models that give eternal repetition, birth after death, sequence after sequence. If those are correct, then endings may not be endings in any true sense, just transformations feeding back into fresh beginnings. The broader message is that the universe's ending is not predefined. It is an open question that shifts with measurements in the present. Every new dataset trying to pin down how dark energy behaves changes what the far future could be. Physicists often say the early universe and the late universe are connected. By learning one, we understand the other. Dark energy sits right between those extremes, shaping both the birth and death of cosmic history. In that sense, studying endings is not about indulging speculation, but about testing physics to its limits. The true nature of spacetime, quantum fields, and fundamental forces all converge on how the universe eventually evolves. That is why simulations of endings are not detached science fiction. They are ongoing investigations into what our best physics demands. No conclusion is yet possible. The data do not privilege one outcome above the others. Heat death, rip, crunch, bounce, collapse, freeze, all remain plausible under some version of evolving dark energy. Far from being settled, the cosmos's fate looks more uncertain in 2025 than it has in decades. But that uncertainty is not a weakness. It signals that cosmology is shifting once again into a new era of discovery. The end of everything may be catastrophic, endless, or cyclical, but right now the precise nature of that end is as unknown as the exact way dark energy works. And with every measurement we gather today, we stretch the horizon of possible outcomes tomorrow. The story of the universe's ending is still being written, one dataset at a time. The universe is not fixed or finished. Every new measurement shows it to be more complex, more active, and more unpredictable than older models allowed. Instead of treating uncertainty as something to fear, it can be seen as the fuel that drives discovery. The gaps in knowledge point the way forward, creating opportunities for ideas that have not yet been imagined. What if the most profound discoveries are yet to come, and the universe holds even more secrets than we can currently imagine? Our understanding of reality may shift again tomorrow, and exploring those shifts is what truly matters.